Earth Systems 3209. Unit 4, the forces within Earth. References for this unit can be found in Chapters 4, Chapter 15, Chapter 16, Chapter 19 in the textbook, and also in Appendix A and Appendix B in the curriculum guide. Unit 4, Topic 2.2. This topic will look at convection and look at its connection to seafloor spreading. We will focus on explaining the mantle convection and how it relates to Hess and Dietz's ideas behind seafloor spreading. When you look at convection and seafloor spreading, to fully understand the theories of continental drift and plate tectonics, you must first have an understanding of the internal processes that occur within Earth. Convection currents in the asthenosphere, as proposed by Arthur Holmes, and the seafloor spreading idea, as proposed by Harry Hess and followed up by Robert Dietz, provides evidence which supports a mobile Earth. By combining the theories of seafloor spreading with continental drift and earthquake information, the new theory of plate tectonics became a coherent theory to explain wide crustal movements. We can find information on this topic in your textbook on pages 527 to 532. Let's focus on convection and how it relates to seafloor spreading. The many plates that make up Earth's crust sit directly on a plastic-like layer within the mantle called the asthenosphere. So this asthenosphere is located in the upper portion of the mantle, and it has the ability to move as a plastic would if it was heated. A scientist named Arthur Holmes provided evidence to support that the tectonic plates move on what he referred to as convection currents. And these convection currents are located within this asthenosphere layer, directly below the lithosphere. Convection cannot take place without a source of heat, and heat within the Earth comes from two main sources. We see heat being generated in the mantle by radioactive decay, and we also have heat within the Earth, which is called residual heat. That's heat that is left over and continually escapes towards the surface as the Earth gets older. If the asthenosphere is in fact moving as a result of convection, then Holmes suggested that the convection could be the mechanism responsible for plate tectonics. In other words, convection could be the mechanism that explains why tectonic plates, the lithosphere, actually moves. Hess was influenced by Holmes's ideas and suggested that deep within the asthenosphere, heated material expands, becomes less dense, rises, and pushes its way up through ridges. It then moves along the base of continents and oceanic plates, pulling the plates in opposite directions. This concept is what Hess called seafloor spreading. When the slowly moving material reaches cooler areas, it tends to contract and sink, causing one plate to move downward, and this is called the subducting plate, beneath another plate, which is called the overriding plate. This material is then recycled back into the mantle. So if we look at Hess's ideas behind plate tectonics and seafloor spreading, we notice that in areas where we have a lot of heat rising, these currents tend to rise upward and they move outward in opposite directions. As the material rises upwards, some molten material will spill out onto the ocean floor through what's called an ocean ridge. But the key is here, the actual movement of the asthenosphere beneath the lithospheric plates. And as it moves beneath the lithospheric plates, it tends to pull the tectonic plates in opposite directions. And this is what Hess referred to as seafloor spreading. So the driving force behind seafloor spreading is the hot rising currents that are located in the upper mantle. As these hot currents move away from the heat source, they tend to cool. And as they cool, they tend to descend down into the mantle once more. Once it descends down, it actually pulls the ocean floor down with it, which is called the subducting plate. And the other plate is pretty immobile, would be called the overriding plate. This forms another feature called oceanic trenches. So Hess proposed that at ridges we see ocean floor spreading away from one another, and at trenches we see ocean floor being subducted down deep into the mantle, where it's actually consumed and destroyed, where it becomes a part of the mantle once more. So these currents then continue its cycle and move back towards the heat source. So these cycles that we find in the asthenosphere is what Hess referred to as convection currents, and it is his mechanism that explains the movement of tectonic plates. During World War II, geologists employed by the military carried out studies of the seafloor, a part of the Earth that has received very little scientific study. The studies of these scientists revealed a couple of different interesting facts. The topographic studies involved measuring the depth of the seafloor. These studies revealed that the presence of two important topographical features were located on the ocean floor. One feature was called oceanic ridges. Oceanic ridges are long winding ridges that occupy the middle of the Atlantic Ocean and the eastern part of the Pacific Ocean. These scientists noted that in areas where ridges are present, the depth of the ocean floor beneath the sea level is not as far as other places along the ocean floor. Scientists also discovered a second feature. These are known as ocean trenches. Deep ocean trenches exist along the margins of continents, particularly surrounding the Pacific Ocean. And scientists noted that the depth of the ocean trenches located beneath sea level is deeper than the average ocean floor. So when we look at further studies at this information revealed by these scientists, the studies of the ocean floor noted that the oceanic lithosphere moves away from the ridge. It cools and sinks deeper into the asthenosphere. Thus, the depth to the sea floor increases with increasing age or distance away from a ridge. Now we can notice this in the diagram down below. The vertical axis indicates depth to the sea floor, where we start off at the ocean sea level at 0 and ranging down to 7,000 meters, which is 7 kilometers depth. So at ridges, we notice that ridges are approximately anywhere from 2,500 to 3,000 meters deep. That's 2.5 to 3 kilometers. And as we move away from the ocean, from oceanic ridges, the deep sea floor can get down to as far as 5,000 to 6,000 meters deep, which is 5 to 6 kilometers deep. And this is noted the farther we move away from mid-oceanic ridges. Because of the oceanic ridges are areas of young crust, there is very little sediment accumulation on the ridges. Sediment thickness increases in both directions away from the ridge, and is thickest where the oceanic crust is the oldest. So if we refer to the diagram below, if we look directly in the location of an oceanic ridge where it forms, we notice that we have very little sedimentation on top or that exists adjacent to each ridge. As we move away from the ridge itself, we notice that the thickness of the sediment also increases in depth. So therefore, sediment thickness will increase in both directions the farther we move away from oceanic ridges. Also, saw another scientific discovery. It says as new ocean crust is created, it is pushed aside in two different directions. Thus, the age of the ocean crust becomes progressively greater in both directions away from a ridge. So scientific studies indicate that the farther you move away from an oceanic ridge, the older both the ocean floor gets and also the older that the sediment will get the farther you move away from an ocean floor. So close to the oceans, we generally get younger sediments and oceanic floor, and the farther we move away, the older the sediment will become and the oceanic floor, the ocean rocks. From these studies, scientists also concluded because the oceanic lithosphere is created at ridges and destroyed at subduction zones, better known as trenches, scientists noted that the oceanic basins is continuously being recycled and are relatively young in age compared to the continents. The oldest ocean crust occurs farthest away from the ridge, and in the Atlantic Ocean, the oldest ocean crust is about 180 million years old. That dates back to approximately Jurassic in age, and this age coincides with the breakup of Pangaea, which occurred at the end of the Mesozoic era. So in conclusion, by studying sediments on the seafloor and looking at the age of the seafloor, we can conclude that the following features can be noticed the farther you move away from an oceanic ridge. Seafloor tends to get deeper beneath sea level the farther you move away from a ridge. Sediments get thicker and older in age the farther you move away from the mid-oceanic ridge. The seafloor gets older the farther you move away from oceanic ridges, and the seafloor is continuously being recycled and is relatively young in age. This recycling occurs when oceanic floor is created or formed at mid-oceanic ridges and is destroyed at oceanic trenches. Let's look at a sample problem that explains the concepts that we just talked about. The question reads, explain why it is impossible for oceanic crust to be older than 200 million years. When we look at the concepts previously discussed, a geologic process called seafloor spreading causes the ocean floor to move. Ocean floor is created at oceanic ridges, and ocean floor is destroyed or consumed within the earth at subduction zones or oceanic trenches. Because of this process of recycling, the creation at ridges and the destruction at trenches, the ocean floor occurs within a span of age of approximately 180 million years to 200 million years old. Therefore, the ocean floor is recycled every 200 million years approximately. Let's look at some other examples from past public exams. Example number 1. First question reads, which earth layer contains convection currents that cause plate movement? So when we look at the movement of the tectonic plates, it's caused by a layer within the upper mantle, and this layer is called the asthenosphere. So the answer to the first question would be A, the asthenosphere. Second question reads, which scientist proposed the idea of seafloor spreading? Seafloor spreading was the idea put forth that the ocean floor is a mobile ocean floor, where it moves apart at ridges and it is consumed back into the earth at trenches. This idea of seafloor spreading was first proposed by a scientist named Harry Hess, and later was supported by another scientist named Robert Dietz. So the answer to this question, the scientist who proposed the idea of seafloor spreading, will be B, Harry Hess. Example number 2. This question reads, why is the ocean floor no older than 200 million years old? So when we look at the age of the ocean floor being created at ridges and destroyed at trenches, the age of the ocean floor is no older than 200 million years old because of answer C. The ocean floor is being recycled as a result of convection currents in the upper mantle called the ionosphere, and because of seafloor spreading. So your answer to this question, ocean floor is no older than 200 million years old, would be C. The ocean floor is being continuously recycled. Your turn. Take the time and complete the following question. You can pause your recording now to prepare your answer, and the solution will follow. Question reads, in the diagram below, at which drilling site will the oldest igneous rocks most likely be found? So if we look at the diagram to the right, we notice that we have an oceanic ridge that exists. That's called the East Pacific Rise, or the East Pacific Ridge, as stated here. We also noted that the farther we travel away from a ridge, the older that the ocean floor becomes. So if we want to find the location of the oldest ocean rocks found on the ocean floor, it will be the farthest point away from the ridge. So in this case, our answer would be A. So in the diagram below, which drilling site would give you the oldest ocean rocks? And the answer would be A. Let's look at the points covered in this presentation. An overview of the points covered include Harry Hess was the scientist responsible for proposing the first ideas behind seafloor spreading. So Harry Hess was credited with the theory of seafloor spreading, where Robert Dietz further supported Harry Hess's discoveries. Seafloor spreading is the driving force, seafloor spreading is driven by convection in the mantle, where tectonic plates move apart at ridges and come together at trenches. So the ideas put forth by Hess and Dietz focused on a mobile seafloor, where seafloor was created at ridges where they would move apart because of the convection currents pulling and moving in opposite directions. And later, the seafloor would be destroyed at trenches where the ocean floor would be consumed back into the mantle. And also discoveries by scientists during World War II indicated some hidden information about the ocean floor. Some facts that they found include seafloor gets deeper the farther you move away from an oceanic ridge. Sediment gets thicker and also gets older the farther you move away from an oceanic ridge. They also noted that the seafloor gets older the farther you move away from an oceanic ridge. And from this, they concluded that the seafloor is continuously being recycled, and it is relatively young in age as compared to the continents.